Okay, physics. Yeah, it's a lot of stuff, a lot of material. So let's start with the latest stuff, chapters 13 and 14. So there's at least a third of the final will be on chapters 13 and 14. So we start with the mass spring system. And we proved that the solution to the vibration of a mass on a spring was either a sine or a cosine wave. It's pure harmonic or simple harmonic motion. It was just a single sine wave. So what we're talking about is either a mass hanging from a spring, or you could think of a mass on a frictionless surface attached to a spring. So this has a certain mass, this has a certain spring constant, and because the force due to the spring is proportional to the spring constant and the displacement, which that's called Hooke's law. And the negative is indicative of the fact that if you have a positive x, so you're stretching the spring, that the force is going to be in the opposite direction it moves. So that's where the negative sign comes from. And by doing Newton's second law on this mass, assuming that the mass of the spring is negligible, you end up with the differential equation, and you solve the differential equation, and you see that x as a function of time is equal to the cosine of 2 pi f times t. And this is assuming this form of the equation, and also you've got x max here, the maximum displacement. So so 2 pi f, and this actually is just the form of an equation for a simple harmonic vibration, which could be sound waves, could be masses on springs. For the particular case of a mass spring arrangement, it's equal to the cosine of the square root of k over m times t. And that square root of k over m is from the solution of the differential equation. That's how you make sure that the differential equation is satisfied. It doesn't matter the frequency that it oscillates. You can see if I set 2 pi f equal to the square root of k over m, you can see that the frequency of oscillation is not dependent upon the displacement. The further you displace it, the further it oscillates, but the actual frequency that it oscillates at is independent of that. So mass, m is mass, k is spring constant, mass has units of kilograms, spring is constant as units of newtons per meter. That gives you units of inverse seconds, which is frequency. So this will give you an answer in hertz. Hertz is a cycle per second. So I could give you some information about the oscillating behavior, what the frequency is of the oscillation, and if I gave you the mass, you could figure out the spring constant. If you gave the spring constant, you could calculate the mass. Also, the period of oscillation, and this relates to any vibration. The period is always 1 over the frequency, not just for this arrangement, but for light waves, sound waves, anything that oscillates. This actually doesn't have a wave, but it's a sinusoidal kind of thing. So look back at the homework, see what problems we had that involved masses and springs. Now another thing we talked about, we did this in class, was a wave on a string. So these are the supports, and this, if you create a small displacement and you let it go, that wave is going to be, that disturbance is going to be propagated down the string. at a certain speed. So this is waves on strings. And even though it's not exactly like this, it's similar because the string has a mass per unit length. So there's this mass per unit length. So if I gave you the mass of a string and I gave you the length, you can calculate the mass per unit length. You might remember in that lab that we did, I measured the mass of the elastic band and then divided by the length to get a mass per unit length. So this is kilograms per meter. And there's also tension. So F is the tension in the string. And that has units of newtons. So force. So relative to over here, you've got this frequency that's related to the square root of k over m. K is kind of like this tension, and the mass per unit length is kind of like the mass part. And it turns out that the wave speed of a wave along a string is equal to the square root of the tension divided by the mass per unit length. Now here we don't have a wave, here we have a wave. So this is wave speed. And if you use newtons for force and mass per unit length for kilograms per meter down here, you're going to end up with units of meters per second, like any speed is. So that's one thing. If I gave you some information about a string, like a guitar string, you could calculate the wave speed from that. Now the relationship between wave speed, and this applies to any wave, whether it's sound wave, wave on a string, is that the wave speed is equal to the wavelength times the frequency. So lambda equals the wavelength. And F is the frequency, just like the frequency for the, so this has units of meters, this has units of hertz, and V has units of meters per second. So if I gave you a string with a certain tension, a certain mass per unit length, you calculate the wave speed, and then knowing the wave speed, then you could relate the frequency and the wavelength through this equation. Now, when you have resonance situations on this string, the first harmonic is going to be something like that. So it's just going to go boom, 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 boom. Again, we saw that in the lab, so hopefully you can visualize that occurring. Well, that's only half a wavelength. This would be a full wavelength. So what we can say is the fundamental frequency is equal to, so how are we going to do that? Well, what you're going to do is you're going to say that the wavelength, which is that, is equal to 2 times the length. So that's the length of the string. In meters. So I give you force, tension, mass per unit length to calculate velocity. With velocity, and then using 2L for the wavelength, then you could calculate frequency. So let's just solve that. So frequency equals it's V over lambda, but lambda is 2L, so you get V over 2L for the fundamental frequency. That's your fundamental frequency. And V is equal to the square root of tension over mass per unit length. And then if you wanted the second harmonic, that's going to, the second harmonic is when you have a wave, standing wave that looks kind of like that. And you can, given some other stuff, and you can, I could give you frequency, length of the string, and mass, speed, and length. You can calculate tension, or you can give you mass, speed, and length, frequency, and length, and you can calculate, whichever one you're not given, you can calculate. So those are the relationships. Wave speed. Now for sound waves, wave speed is, so let's just talk about sound waves. So sound waves are not that much different. Instead of calculating it from the tension and the mass, speed, and length, there actually is a way of doing it based on the elastic properties of air, but we're not worried about that in this class. What we do know is that the speed of sound is going to be equal to 331 meters per second divided by the square root of the absolute temperature divided by 273 Kelvin. So when you do calculate the wave speed, sound wave speed, T is temperature in this case, not tension, and it's going to be the absolute temperature, so it has to be in Kelvin. So if I give you it in C, you got to convert to Kelvin. So you can see at 273, the speed of sound is 331 meters per second, because that's when this is 273 divided by 273 is 1, square root of 1 is 1, and you get that. Okay, so that's the speed of sound in air. What else can we say is the same? Well, V is equal to lambda times F. So this again applies for any waveform. Waves on strings, sound waves, light waves. And let's see what else there is. So in the case of sound waves, you've got two scenarios. You've got a tube open at both ends, and these look the same when you draw them, but you've got to realize that these are open to the air. So we'll say this is open and this is closed. And what we said was that you get a node in the middle, and you get antinodes at the ends. So if you were to plot, pressure variation, you would get something like something kind of like that, where in the middle you're just at zero pressure variation. At the ends, you vary from below and above the atmospheric pressure. So that would be the other side of the vibration in terms of the value. So in terms of how many wavelengths, it's kind of like the string wave on a string, except here you're restricted. You still have half a wavelength, and the same is true here. So what you can say is that the wavelength is, and again it's the fundamental frequency, is equal to the fundamental wavelength is going to be equal to 2 times L, the length of the tube. So given the dimensions of the tube, you could figure out what the wavelength is. Given the wavelength and the speed of sound, you can calculate the frequency. You can put them together. So if I take this equation, V equals lambda F, and for this thing open at both ends, and I solve for frequency, frequency equals V divided by lambda, but lambda is equal to 2L, so I get 1 over 2L times V. You get this from the temperature. You're given that in terms of dimensions. That's your fundamental frequency, and then your second harmonic is going to be 2 times the fundamental, and the third harmonic is going to be equal to 3 times the fundamental frequency, and etc., etc. So that's the case for a tube open at both ends. For a closed tube, if you plot the pressure, what's going to happen at the end, there's no variation because it's a solid wall, but at the other end it varies. So what we call this a node. just like we call that a node, and this is called an antinode. So in this case, for this one, lambda is equal to 4 times L, because it takes 4 lengths to get 4 lengths of the tube to get a full wavelength. So this still applies, but the fundamental frequency, which is V over lambda, you plug in for lambda, you get 1 over 4L times V. So with a tube closed at one end, you're going to get your fundamental frequency is going to be half of what it is for a tube open at both ends. But the difference here is that there is no second harmonic. You have the third, so that's 3 times 1 over 4L times V, or 3 over 4L times V, and then the fifth harmonic is 5 times 1 over 4L times V, which is 5/4. So those are the differences between the two. So you can't take the fundamental frequency for a tube closed at one end and open at the other and just multiply it by 1, 2, 3, 4, 5. You actually have to take this number, this value, the fundamental frequency, and multiply by 3, 5, 7, 9, all the odd numbers. So again, look back at your homework, be able to calculate the information of the frequencies and the harmonics for tubes open at both ends and tubes open at one end. Okay, then we have the Doppler effect. And what that is the change in perceived pitch due to the relative motion between a source and an observer. And it comes down to the frequency of the observer equals the frequency of the source, which is determined by whatever frequency that the source vibrates at, like a speaker. And then you have this ratio V, the speed of sound, and you either have plus or minus the so let's think about this. Just using experience. Let's say here I am, the observer. So that's me, the observer. Here's the sound. That's the source. So if I want to, if you have this guy coming towards you, then you hear a higher pitch because the sound waves get smushed up. So I need to have this so when V sub S is positive, and this is 0, that the frequency you get is higher. So to do that, we could subtract V of the source. Excuse me. I'm just going to pull out my book here, make sure I do this right. The important thing is to just do it in the direction to give you the pitch that you expect. So whatever you do to make the relative velocity of the two come together, that will be the one that will result in a higher pitch. And if they're moving apart, then you get a lower frequency. So I'm going to copy this. Excuse me. Yeah, okay, so I did it right. I just want to check. And then if the observer is moving, so this is moving towards the observer, this is a positive quantity, and you subtract it. And up here you have plus the velocity of the observer. So what happens is, so the positive speed is substituted for V0 when the observer moves towards the source. So if I'm moving this way, the source is stationary. It's the same effect, and you essentially while these guys are moving towards each other, whether this one's stationary and this one's moving and this one's stationary, this one's moving. The effect is to increase the frequency. So by saying when the observer approaches the source, then you add that onto there. And yeah, it's just getting the sign correct, but just remember that you do what you need to do as far as the signs are concerned, so that if you have the source moving towards the observed frequency is higher. So that means subtracting a number from here or adding a number to there. If say the source is past and is leaving, then you're stretching out the sound waves. So you want to make the frequency observed lower. To do that, you would have this be negative, so the denominator would become bigger, rather than remembering some crazy sign convention. Just think about a fire truck going by. Okay, so watch the video on that. Look at the homework. And the last thing here about sound, I think, what is the last thing about sound? Actually, that may be we talked about B frequencies, but I'm not going to put anything on about B frequencies. We didn't talk about sound intensity enough. I realized we didn't talk about it at all, so we're not going to talk about decibels and watts per meter squared. So that's chapter 13 and 14. So right now I have, let's see how many problems I have on I have 10 problems on the final. And there's 1, 2, 3, 4 problems to do with chapters 13 and 14. So let's go back to the beginning now. So we had calculate forces, electric fields, and voltages. So what I would suggest is you watch the first review for the first test. That was where we had the charges lined up in a row. And you can look at the first test, the problems like that. I'm not going to redo it here since I've done it before. Okay. Also in that first part was finding equivalent capacitances and resistances. So what we're talking about there is I'm going to give you some circuit that has a battery and a bunch of resistors or capacitors, and you have to use the rules. So depending upon whether they're in parallel or series, you have to go through multiple steps in simplifying them. But for capacitors, the equivalent capacitance is in parallel. It's just the sum of the individual capacitors. And for the series, it's 1 over. So don't forget to take the reciprocal when you get to the end. When you take the reciprocal of these capacitances, then you get an answer. They have to take the reciprocal to get the equivalent capacitance. So those are the rules for replacing multiple resistor or multiple capacitors with a single capacitor. And the rules for resistances are exactly the opposite. So the equivalent resistance of series resistors is the sum of the individual ones. Should I say parallel? Sorry. So there you have 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So I'd suggest you go back, look at your test. If you know what you're doing, just review a little bit. If you messed it up, then you might want to review it or talk to your friends about it. So you'll, like I said, you'll have something that looks like this, where you've got multiple resistors or capacitors, and I ask you to replace those with just a single resistance, and then you could calculate the current. For this case, for capacitors, you calculate the charge. I'm not going to ask you to go back and find the individual values, so it's similar to what we saw in the tests. Now, there is these relationships for the different kinds of elements. So you've got Ohm's law for resistors, and what that says is that the current is going to be through a resistor is equal to the voltage divided by the resistance. So for a given voltage, a higher resistor means that it's going to reduce the current. So that's Ohm's law. You can have it in different forms depending upon what you solve for. So these are the 3 possibilities. Current is voltage over resistance. Resistance is voltage over current, and voltage is equal to current times resistance. So where did we use this? If I gave you a length of wire, L, and I wanted to choose, and I give you an area somehow or another, or I could give you a radius or diameter, and then you could assume that it's circular. So the area of a circle is pi r squared. So if you have the radius of the radius of the wire, the diameter of the wire, you can calculate the radius, and then you can calculate the area. And with the area and the length and the resistivity, so remember this, the resistance of an element is equal to the resistivity times the length divided by the area. So this is resistance in ohms. This is resistivity, which is, so this has units of ohms. This is resistivity, which is a physical property, and it has units of ohms meters. This is the length of the wire. That's units of meters, and the cross-sectional area, which is how you would calculate that. That's in meters squared. So you can see ohms meters times meters is ohm meters squared divided by meters squared is ohms. So that all works out. So then I might ask you, how much current can flow through this wire given the properties, the resistivity, the length, and the area. You can calculate the resistance, and then you could calculate the current by taking the voltage across here and divided by the resistance you've calculated through there and get the current. Besides just using it with a given resistance value, maybe you have to calculate the resistance for some reason. So that's Ohm's law. Then you have capacitors. And we had a problem like this on the test where you had to calculate the capacitance for a parallel plate capacitor. So you've got 2 plates, you've got these leads, this is minus, this is plus. What happens is you get an excess of electrons over here, and you get a deficit of electrons, which make it positively charged. And the capacitance of that is just equal to mu0 times A divided by D. And I'll give you mu0. Actually, that's epsilon 0, not mu0. Epsilon 0 So that's a constant. Epsilon 0 is, what is it? I give it to you somewhere here. It's like 10 minus 12 something or other. So the permittivity of free space, which is what that thing's called, is 8.85 times 10 to the minus 12th coulombs squared per Newton meter squared. So if I give you the area of a capacitor, you know this, divided by the distance between the plates. So this is the area, meters squared. This is the distance, not diameter, distance in meters between the plates. And this gives you the capacitance. Now if you had a dielectric material between the plates, then you'd be able to get more. So that's how you calculate capacitance given the physical characteristics. Just like here, you can calculate the resistance given the physical characteristics. And then you have the relationship between capacitance and not current and voltage, but charge and voltage. So that's the numerator is charge, which has units of coulombs, and the denominator is voltage or potential, that has units of volts. So it's charge per volt. It's saying the larger the capacitor, the more charge you can put on the plates for a given amount of voltage. So again, look at the problem from the previous test where you had to manipulate, calculate. And finally, it turns out you can use Gauss's law to figure out the electric field. The electric field between two parallel plates for capacitors equal to the voltage across the plates divided by the distance between the plates. So it's irrespective of the actual capacitance. It's just equal to the voltage applied divided by the distance between the two. Same distance here in meters. Now, let's see if there's anything else. Oh yeah, Kirchhoff's laws. So we did this, I might have done this as an extra credit problem or something, second part, but it's on the exam, Kirchhoff's laws. So you again, go back and look at your previous tests. This is where you're going to use a matrix operation to solve your problem. So what I do is I give you some kind of circuit that has resistors, and it has some kind of voltage, source, and it may be multiple more than one voltage source. So I'm giving you these resistors and given these voltages. If you look on your memory stick, there should be a description of using Kirchhoff's laws. The two laws are the voltage law that says the sum of voltages around a loop is 0, and what you do is you look at various loops in this circuit, and then you have the current law or the junction law. So this is a voltage or a loop law, and this is the current law. The current law says the sum of currents into a junction is 0. So this is where I1 plus I2 minus I3 equals 0 kind of thing. So the current laws, the junction laws, always involve just the currents. The voltage laws, you have to look at the voltage change across the resistors. Remember, we assume some direction of the currents, the unknown currents, and then we use Ohm's law to calculate what the voltage drop is, current times the resistance, and then so you're going to end up with equations associated with the loops and equations associated with the currents. Remember, there's one less, there's the number of current equations is one less than the number of junctions. So in this example here, this is a junction, this is a junction, this is a junction, and that's a junction. So we'd only use 3 out of the 4, and then we'd make up the rest of the ones that are needed by doing the appropriate number of loops. Again, just letting you know it's on the exam, but you're going to have to go back and remember how to do that. It would be nice to not put any phasor stuff on the final. Okay, now if you have a resistive element like a hairdryer or of an oven, there's the relationship between the power consumed, P power, and the voltage and the current. And this actually applies for any element, whether it's resistive or not. So this is just the definition of power is voltage times current. But for a resistive element, it's equal to I squared, the current squared, times the resistance. And that should be power, not R. And the other one is power is equal to V squared over R, which is, again, these two are for resistive only. And this one is always. It's true. Now, a lot of times we have, we have time varying currents like this, power consuming currents like that. So this is current, say, or voltage. In that case, the power is not the instantaneous voltage, but you use the RMS. So remember, power is equal to the RMS voltage times the RMS current, and the same thing down here. It's going to be I RMS squared times R. So the resistance is just a constant, doesn't matter whether it's DC or AC. And the relationship between the maximum voltage for a time varying signal and the RMS is that factor of the square root of 2. So the RMS voltage is going to be equal to the maximum voltage divided by the square root of 2, and the same thing for the current. The RMS current stands for root mean square, is the maximum. So if I say it's RMS, you just can use it directly. If I told you the maximum voltage of the time varying voltage is something, then you have to divide by the square root of 2 to get to the right units to calculate the power. So this is for DC circuits. This is for AC circuits. Sometimes we use this in conjunction with Ohm's law to solve everything that we need to solve for. Okay, I'm just looking through to see if there's anything else I need to tell you. Oh, yeah, and then the last thing, just have available the forces due to moving charges. So you had the force, this is a point charge. So this could be like an electron or just a charge, anything. The force is equal to the charge. So it might be the charge on an electron or proton times the speed of the electron times the magnitude of the magnetic field, and then you've got this angle. So let's say this is the velocity of the particle and the magnetic field strength is going that way. And if these are perpendicular to each other, then you get the maximum. So if this angle is 90 degrees, you get the maximum amount. So that would be the sine of theta, where theta is the angle between the magnetic field vector and the velocity vector. For the most part, we've been doing it where the velocity is perpendicular to the magnetic field, and therefore you get 1 when you do this. So it simplifies down. So this is, again, charge, which would be in coulombs. This would be speed, meters per second. This is Tesla, magnetic field strength. Then you have a wire, and the force on the wire is going to be equal to, so what do you have? You have charge, you have the length of the wire, you have the magnetic field, and you have this sine of theta. So this is, I is the current in amps. This is the length of the wire in meters. This is the magnetic field strength in Tesla. This is the angle. Again, this is the direction of current. This is the direction of the magnetic field. The angle between the two is theta. A lot of the times that angle is 90 degrees to maximize the force. And you just have current times length times magnetic field strength. And then you have the torque on a loop. So we have some current going into a loop like this. So there's a current flowing. And then there's, let's say this is dimension A. This is dimension B. And so the area of the loop is just A times B in this case, because it's rectangular. If it's circular, it'd be 2 pi times the radius. And the maximum torque is going to be equal to, so you have the area is one of the numbers. You have the magnetic field strength, and you have the current. And then you have an angle, but for the maximum torque, you don't have the angle. So it's just current times magnetic field strength times the cross-sectional areas associated with that loop. And this gives you units. Where you guys messed up was Newton meters, because a torque is a force acting through a distance. So that's the forces due to moving charges in different ways. Point charge, wire. This is where we have a charge moving through a loop, which gives a torque. And I'm not going to, just to put your mind at ease, I'm not going to ask you to use Faraday's law or to do phasors, which I already mentioned. So the only thing, what you need to do is go back and look at the previous tests for the 6 problems that are not associated with vibrations and sound. Make sure you know how to do those. Make sure you know how to do Kirchhoff's laws. And the key thing there is just keep your signs correct when you're looking at the voltage drop or increase across resistors, depending upon which way the current's flowing relative to the loop that you create. Okay, that's all I'm going to tell you.